Network design. Have you ever wondered what goes on behind the scenes when you seamlessly connect to Wi-Fi or video chat with a colleague across the globe? These daily networking feats couldn't happen without meticulous planning and design. Welcome to the Network Design module. In this module, you'll learn how understanding network design empowers IT support technicians to keep infrastructure running smoothly. You'll explore how physical and logical network topologies form the backbone of effective networks. You'll also learn about designing networks for security, resiliency, and scalability. Finally, you'll discover the different types of documentation to create during the network design process. Learning objectives. After completing this module, you should be able to explain the characteristics and configurations of common physical and logical network topologies. Choose a network topology given a scenario. Select design principles to ensure a computer network is secure, resilient, and scalable given a case study. Describe the benefits and components of network design documentation, including network diagrams, networking hardware configuration files, and policies. About this lesson, network topologies. In this lesson, you'll get an introduction to network topologies and how they provide the blueprint for data flow across physical and logical network components. You'll learn about the steps in the network design process. Then, you'll explore common physical topologies like bus, star, ring, mesh, and hybrid designs. Finally, you'll learn about different types of logical topologies that determine how data moves between connected devices. The network design process. Page 1 of 2. Video transcript. Network design. Meet Rajiv, an IT support technician who leads the IT team at a flourishing small company. Exciting times are ahead. The company is opening 2 new branches in different regions. As the company's head of IT, Rajiv is responsible for designing the network for these 2 new locations. To design the network, Rajiv follows a 6-step process. Gathering requirements. Selecting a network topology. Considering network design principles. Choosing network hardware. Documenting the network. Testing and validating. First, Rajiv must gather requirements. To do this, he talks with stakeholders at his company and reviews data. He needs to understand the company's needs, the number of users, the types of data, and anticipate future growth for the company. In step 2, Rajiv must select the right topology. But what is a network topology? A network topology is the layout of how different network devices and components are connected. He considers the 5 primary physical topologies: bus, star, ring, mesh, and hybrid. Each topology has its strengths and weaknesses. So, Rajiv must choose wisely, considering the company's requirements and budget. In step 3, Rajiv must consider the basic network design principles. These include scalability: can the network grow? Resiliency: will the network recover from issues? And security: is the data safe? Rajiv considers all the factors and requirements for this project. Based on his experience, he chooses a star topology for the network. Now, Rajiv needs to select the right hardware for the network. Rajiv chooses networking hardware carefully, ensuring there's no single point of failure that could affect the whole network. Every device has a specific role in maintaining a seamless and secure connection. Rajiv's next task is to document the network design in a network diagram. A network diagram illustrates how different network devices and components connect and interact with each other. Page 2 of 2. Finally, testing and validation are vital before implementing the new network design for this company. Rajiv simulates the network to ensure all components communicate flawlessly. Now that he followed the 6 steps in the network design process, Rajiv can help his company expand and ensure employees stay well connected. What do you think? Employability skills. Growth mindset. Which step of the network design process are you most interested in exploring more, and what draws you to it? Evaluate your thinking. Does your answer account for the following? 1. Gathering requirements. Do you enjoy engaging with colleagues, stakeholders, and departments to understand their needs? This step involves a lot of communication and relationship building. Are you drawn to sifting through data, reports, and projections to ascertain requirements? This phase is about piecing together the bigger picture from various data points. 2. Selecting a network topology. Are you interested in understanding how different components communicate? Selecting a topology requires mapping out efficient pathways. 3. Considering network design principles. Do you like thinking about the long-term implications of decisions? In this step, you'll need to ensure scalability and future-proofing. You will also need to identify potential challenges and threats the network might face and consider how to address them ahead of time. 4. Choosing network hardware. If you're drawn to understanding the essence of tech equipment, their functionalities and specifications, this step will be of interest. 5. Documenting the network. If you enjoy documentation, ensuring clarity, and creating resources that others can understand and follow, this is a great step to learn more about. You might also be interested if you have strong organizational skills, as this step requires systematically laying out the network details, ensuring easy accessibility for future references. 6. Testing and validating. Do you enjoy simulating scenarios to ensure everything works as expected? This step is all about identifying and rectifying potential problems. And, if you appreciate gathering data and making iterative improvements, this phase would involve a lot of that, ensuring the final network is robust and efficient. Introduction to network topologies. Imagine you are an urban planner with the responsibility of designing new highways for a big city. You must consider a variety of factors to make sure traffic flows smoothly. For example, you'll need to anticipate where the heaviest traffic might occur at different times of the day, where traffic jams might develop, and how traffic patterns change during special events or seasons. In addition to understanding traffic flow, you'll also need to develop a detailed blueprint of the highway's infrastructure. This blueprint will include the design and location of on-ramps and off-ramps, the placement of traffic lights, and even the dimensions and materials for road signs. You must plan every small detail in advance to ensure the road system functions as efficiently as possible. Cars merging from two side roads onto a main road with cars. Network engineers design networks in a similar way. They carefully plan how data will travel from one point to another, considering potential areas where data traffic might get congested. Just as in urban planning, they also develop a precise blueprint of the network's architecture. This step includes specifying how to configure and interconnect different components like servers, routers, and switches. Network engineers rely on network topologies to provide a structured approach to network design. A pencil writing next to a network of a laptop, a LAN, a computer, and a server. Network topology refers to a structured layout that outlines both the physical and logical components of a communication network. Topologies are the blueprints that show how different components in a network connect and how data will flow through these components. These components can include computers, servers, routers, and other devices that communicate with each other. There are two key types of topology. Physical topologies that describe how devices are physically connected. Logical topologies that describe how data flows between connected devices. Physical and logical topologies serve as two integral but distinct aspects of a network's architecture. Physical topologies function like roads in a city, serving to connect devices. While logical topologies act like traffic rules, describing how data flows between those devices. Both are essential for network performance and resilience, yet each offers unique advantages and challenges. For IT support technicians, understanding network design and topology helps them quickly isolate and resolve network-related problems, such as bandwidth issues, connectivity issues, and data packet collisions. IT support technicians might receive support requests from employees who can't connect to the internet or have video conferencing issues. Understanding how networks are designed, along with their different topologies, allows technicians to provide precise, understandable solutions, improving the overall customer experience. This foundational knowledge also allows IT support technicians to optimize network systems. Technicians can use their understanding of network structures to proactively suggest hardware or software upgrades, tweak settings for better performance, or even advocate for a change in network topology. By understanding network design and topologies, they can help align the network's performance with the organization's evolving needs. Next, let's take a look at some common network topologies. Common physical network topologies. Overhead view of 3 people working at desktop computers and wearing headphones. While every network is uniquely designed, most network designs are based off some common physical network topologies. A physical network topology is the structure of the physical components of a network, such as client devices, servers, routers, switches, and the cables that connect them. Knowledge of these common topologies can help IT support technicians better understand the underlying structure of the networks they are working on. The 4 main types of physical network topologies are bus, star, ring, mesh. Additionally, there is a hybrid topology that combines elements of at least 2 types of these network topologies. Let's explore these topologies in more detail and learn about their advantages and disadvantages. Bus topology. In a bus topology, all computers connect to a single central cable, often known as the bus. This cable runs the entire length of the network. Data transmission in a bus network uses a process known as broadcasting, which is when a device sends a single data transmission to all potential receivers or destinations within the network. In a bus topology, broadcasting involves transmitting data onto the bus, where all devices on the network can see it. However, only the device with the matching address processes the data, while the others ignore it. One advantage of a bus topology is that the network is easy to understand and simple to set up. However, a disadvantage is that a bus topology has limited scalability and is vulnerable to collisions, which can lower performance. Another disadvantage is that a failure in the central cable can disrupt the entire network. Notice in the following diagram that there is a central line representing the bus cable and other lines representing connections to multiple laptops and desktops. Star topology. In a star topology, all devices connect to a central hub or switch. In this topology, data transmission occurs through the central hub or switch, and each device communicates directly with the hub or switch rather than with each other. Hubs are simpler and less intelligent, while switches are more advanced and capable of making decisions about how to route data to its destination. An advantage of a star topology is that it's easy to implement. Administrators can add or remove devices without affecting the network, and a single cable failure doesn't affect other devices. However, there are some disadvantages. Star topology's hub, or switch, is a single point of failure. This means that if it fails, it affects the whole network. Star topology can also be more expensive than a bus topology because it requires more cables. Notice in the following diagram how multiple laptops and desktops connect to a central router by other lines, representing logical network connections, in a star configuration. Ring topology. In a ring topology, each device connects to exactly 2 other devices, forming a ring. Data travels around the ring in one direction, from one device to another, until it reaches its destination. Each packet of data travels around the ring, and each device examines the packet to see if it is the intended recipient. If the device is not the intended recipient, it passes the data packet along to the next device in the ring. When the data packet reaches its destination, the receiving device removes it from the network. A ring topology is simple to install. The ring structure also reduces the opportunity for data collisions because data packets travel in a predictable direction. However, failure in any cable or device disrupts the entire network. Adding or removing devices can be disruptive, as it requires temporarily disconnecting the entire network. Notice that the following diagram shows multiple laptops and desktops connected to each other by lines, representing logical network connections. Notice that the network structure is in a ring configuration. Mesh topology. In a mesh topology, devices connect to multiple other devices, not just one. This creates a web of connections that offer multiple pathways for data transmission between any two devices in the network. In a mesh network, data can take multiple possible paths to reach its destination, unlike in simpler topologies where there's only a single route. When a data packet needs to travel from one device to another, network protocols determine the most efficient path, considering factors like the number of hops and current network load. The two types of mesh topology are full mesh and partial mesh. In a full mesh topology, every device connects to every other device. This provides the highest level of redundancy but is the most cable and hardware-intensive option. In a partial mesh topology, some devices connect to all others, but some only connect to the ones with which they exchange the most data. This is often a more practical solution, offering some redundancy without the complexity and expense of a full mesh. A mesh topology is highly reliable as the network can remain operational even if a cable or device fails and when adding and removing devices. However, mesh topology networks can be complicated to set up, manage, and troubleshoot because of the numerous connections. Notice that the following diagram shows multiple laptops and desktops connected to each other by lines, representing logical network connections in both a ring and star configuration. Hybrid topology. A hybrid topology combines elements from two or more different topologies, like star and ring, into a single network. The aim is usually to maximize the strengths and minimize the weaknesses of the individual topologies involved. A hybrid topology allows for the benefits of multiple types of arrangements. However, it is complex to design and expensive to implement. The following diagram shows two sets of devices, desktop and laptop computers. One set is in a ring configuration with lines representing logical network connections, and the other set is in star configuration with lines representing logical network connections connected to a central router. Notice that both sets of devices connect to each other by a router that is placed between them. Next, let's check out common logical network topologies and how data flows between devices. Common logical network topologies. The relationship between physical and logical topologies is not always one-to-one. One physical network topology can support various logical network topologies. A man looking at monitors displaying a map of the world and lines for data flow. A logical network topology describes how data flows between physically connected devices. The combination of physical and logical topologies allows for flexibility and customization, as a logical topology can be modified without altering the physical topology to meet business requirements, such as manageability or scalability. Knowledge about common logical topologies can help IT support technicians better understand how data flows between devices on their networks. The four main types of logical topologies are: point-to-point topology, client-server topology, peer-to-peer topology, virtual local area network, VLAN. Let's explore these different types of logical topologies in more detail and learn about their advantages and disadvantages. Point-to-point topology. A point-to-point topology establishes a dedicated link between two networking devices, enabling them to communicate exclusively with each other. This is one of the simplest types of logical network topologies, and organizations often use it for transmitting data between two locations or for setting up secure, high-speed data transfer channels. Data flows directly between the two connected devices without the need for additional network equipment like switches or routers. Notice that the following diagram shows a laptop and a desktop connected by a single line, representing a logical network connection, bringing 2 points, or devices, together with data traveling between the two devices. A diagram of a point-to-point topology showing a laptop and a desktop connected by a single line, representing a logical network connection with an envelope between them that represents data traveling on the lines connecting the devices. Let's get familiar with the advantages and disadvantages of a point-to-point topology. Advantages of a point-to-point topology. With only two devices on the network, data transmission is fast and often more secure, as there are no intermediate points where the data can be intercepted or altered. It is easy to configure and troubleshoot due to its straightforward nature. Disadvantage of a point-to-point topology. A point-to-point topology is not practical for larger networks as it would require setting up an additional dedicated link for every pair of devices. Client-server topology. A client-server topology is one of the most widely used network models, especially in corporate and enterprise settings. In a client-server topology, one or more centralized servers provide services, resources, or data to client machines such as desktops, laptops, and mobile devices. The servers handle the brunt of the network's computational tasks, while the clients act as consumers of these services. Data flows from the server to the client and vice versa, but it's usually the client that initiates requests. When a client needs a particular service, like accessing a website or retrieving a file, it sends a request to the relevant server. The server processes the request and sends back the required data or service to the client. You'll notice in the following diagram that multiple laptops and desktops are connected to each other by lines, representing logical network connections which connect to a central server. Let's get familiar with the advantages and disadvantages of a client-server topology. Advantages of a client-server topology. Client-server networks are easily scalable, allowing for new devices to be added without affecting network performance. Centralized servers also simplify tasks like updates and troubleshooting, eliminating the need to adjust each client device separately. Disadvantages of a client-server topology. Client-server topologies can have challenges with network congestion if too many clients are attempting to access the server at the same time. If the central server fails, it can disrupt the whole network. Peer-to-peer topology. In a peer-to-peer topology, each computer connects directly with any other computer on the network without needing a centralized server. These peers share resources like files or processing power directly with one another. In this topology, systems share data directly. Each device can both request and provide resources, making data transmission quite straightforward. In the following diagram, multiple laptops and desktops are connected to each other by lines, representing logical network connections. You'll notice they connect to the computer next to them and other computers in the network. Let's get familiar with the advantages and disadvantages of a peer-to-peer topology. Advantages of a peer-to-peer topology. A peer-to-peer topology is simple to set up and doesn't require specialized hardware like servers, and new peers can easily be added to the network. Disadvantage of a peer-to-peer topology. The absence of a centralized server makes network-wide security policies harder to implement and requires that each device manage its own backup and recovery. Virtual Local Area Network, VLAN. In a VLAN, devices in different physical locations can behave as if they're in the same physical network through software configurations. A VLAN groups devices based on logical criteria, such as business function, rather than physical location. Devices within the same VLAN can communicate as if they are on their own isolated network, even if they have no physical connection. For example, all the devices belonging to the finance department might be part of one VLAN, while the marketing department could be part of a different one, even if they all share the same physical network switches or cabling. The following diagram shows laptops and desktops in two different regions in the world. Notice that the two regions are connected by a line, representing a logical network connection. Let's get familiar with the advantage and disadvantage of a VLAN topology. Advantage of a VLAN topology. A VLAN topology increases network performance and security by grouping devices functionally rather than physically. Disadvantage of a VLAN topology. A VLAN topology requires careful configuration and management to ensure proper functioning. Designing a network. A server connecting to a secure laptop. A dotted line is coming from out of the laptop and connecting to the server. The line represents a logical network connection. The design of a network can influence operational efficiency, scalability, and security. These factors are important when designing and configuring both a personal network and a network for an organization. Designing an effective network topology for an organization requires combining technological considerations with an understanding of business needs. When designing a network for an organization, business needs often drive the choice of a particular network topology. For instance, a bank might prioritize security and data integrity, choosing a topology that offers robust security measures and backup and recovery systems. In contrast, a marketing agency that relies on seamless collaboration between departments might choose a topology that emphasizes easy sharing of large files. Understanding these requirements is crucial for aligning the network's performance with organizational goals. Who decides the network topology? Typically, network topology is a team decision involving network architects, engineers, and managers. Even though IT support technicians usually aren't involved in the initial design of a network or the selection of its topology, they need to understand the factors that influence these decisions. This knowledge helps them identify what parts of the network might be more prone to issues that they should prioritize during troubleshooting. It also guides technicians on where to focus their efforts when resolving network-related problems, such as data collisions or network outages. People sitting at a desk using computers and talking. 2 people are in front of the desk at computers, and 2 people in the back of the desk. 1 person has a word bubble above their head. Physical design considerations. A database connecting to laptops, computers, and mobile devices. All the devices are connected to a central server by lines representing logical network connections. As you've learned, physical topologies, such as star, bus, ring, and mesh, come with their own set of advantages and disadvantages. Organizations must consider technological, physical, and business needs when designing a network. Organizations that depend on fast, reliable networking might choose a particular topology because it ensures the network will meet their requirements. Other organizations might find their choice constrained by budget or by the location of their offices. These constraints require organizations to prioritize when choosing an appropriate type of network topology. Examine the following list to learn about key factors that organizations consider when choosing a type of physical network topology. Scalability. For organizations planning rapid expansion, a star topology can be more suitable, given its ease of scalability. Reliability. In organizations where downtime can result in significant losses, reliable topologies, such as mesh or hybrid topologies, are more suitable. Cost considerations. Organizations need to consider the financial investment needed for hardware, cabling, and maintenance. Bus topologies are generally more cost-effective but come with limitations. Physical constraints. Limitations like office space or geographic location can dictate the feasibility of certain topologies. For instance, a bus topology might be more suitable for a single-floor layout. Variable needs. Many organizations need their network to service several needs. In these situations, hybrid topologies might provide the most ideal solution. Logical design considerations. Each logical topology has distinct features that influence data flow and communication protocols within a network. Much like physical topologies, specific business needs often guide the choice of a logical topology. Some organizations prioritize secure and robust data transfer, while others might emphasize flexibility to accommodate varying traffic patterns. These varying priorities play a crucial role in the selection of an appropriate logical topology. Laptops connecting to a cloud icon that connects to databases next to a shield with a check mark. Examine the following list to learn about key factors that organizations consider when choosing a type of logical network topology. Data volume. For data-intensive operations, specific logical configurations are better at efficiently handling heavy traffic. For example, a point-to-point topology is often more suitable for quickly transferring large volumes of data between 2 specific locations. Security. Organizations dealing with sensitive information can require stringent security protocols, affecting the choice of logical topology. For example, a client-server topology is generally more secure as it allows centralized control over security policies and easier monitoring. Operational flexibility. businesses that anticipate frequent changes in network size or structure find certain logical topologies more adaptable to their needs. For example, a peer-to-peer topology is easier to modify and expand, making it more flexible for smaller businesses or projects with fluctuating network requirements. Interconnectivity: business units often need to collaborate seamlessly, thus, logical configurations must facilitate easy communication across different departments or branches. For example, they can configure a VLAN topology to allow secure, efficient communication between different departments within the same physical infrastructure. Next, let's explore some examples of how the needs of a business might determine the network topology design. Scenario: how business needs drive network design. Here's a scenario you can follow to learn about how business needs drive the design of a physical topology and logical topology for a network. Business needs. In the bustling offices of a growing healthcare provider, a network architect named Susan faces a complex challenge. The healthcare provider is expanding rapidly, opening new offices in many different cities. It needs a centralized patient management and appointment booking system, so the IT management team asks Susan to design a network topology that is fast, reliable, and fail-safe. A woman sitting at a desk and working on a laptop. Physical topology: choosing the star for scalability and reliability. Susan immediately thinks about the physical aspect of the network. The healthcare provider needs to use a topology that is both scalable to accommodate new offices and reliable to keep their patient management and appointment booking systems running smoothly. After much deliberation, she decides on a star topology. In this setup, all devices will connect to a central hub, which will then connect to the main headquarters. The star topology also allows for easy expansion. When a new office is set up, it can simply connect to the central hub at headquarters. Moreover, this topology is reliable and includes fail-safes. If one cable breaks down, it won't affect the entire network, only the single connection. Given that the organization's daily operations are critically dependent on the network, this is a major factor in her decision. Logical topology: opting for robust data flow and security. Next, Susan must decide on the logical topology design. The requirements are clear: the patient management and appointment booking systems in every office must communicate instantly with the central server and the Internet. Speed is of vital importance. Security is also critical because the organization cannot have confidential patient data falling into the wrong hands. Susan opts to use a logical client-server topology with an added layer of encryption protocols. In this design, individual workstations, or clients, request resources or services from the centralized hub or the server. The server processes these requests and provides the necessary data or services back to the clients. This kind of logical topology is effective for quick data retrieval and allows for easier management and updates. However, because of the sensitive nature of the information involved, simply adopting a client-server topology is not enough. Susan decides to integrate an additional layer of encryption protocols to the network. Encryption is a method that converts data into a code to prevent unauthorized access. These protocols will ensure that the data remains confidential during transmission, adding an extra barrier against potential intruders. By combining a client-server topology with strong encryption, Susan designs a network that is both fast and secure, fulfilling the demanding requirements of a healthcare management system. Balancing business needs with technical requirements. Susan's choices for physical and logical topologies align with the organization's business objectives. The physical star topology offers the scalability and reliability the organization needs for its expansion. The logical client-server topology ensures that data can flow seamlessly and securely. About this lesson, designing a robust network. In this lesson, you'll learn about the elements that make up a robust network: security, resiliency, and scalability. You'll examine potential security threats to network hardware and traffic, like firmware attacks, device spoofing, eavesdropping attacks, and hijacking attacks. You'll learn about various design network principles that organizations employ to ensure their networks are secure, resilient, and scalable. Finally, you'll review a case study to examine the design principles and recommend additional design principles. Network design principles. Network design principles are a set of best practices and guidelines that provide the framework for planning and creating a network that is both effective and secure. These principles guide the network's architecture, including its physical layout and the logical interactions between various components. The importance of a well-planned network design cannot be overstated, as it significantly impacts an organization's efficiency, data security, and overall operational success. An illustration of devices connecting on a network. All the devices are connected to a central server in a cloud by dotted lines, which represent logical network connections. You learned choosing an appropriate network topology is a key principle of network design, but there are other elements to consider while designing a network. These elements include security, resiliency, scalability. Each of these elements has different guidelines and best practices. By carefully considering each of these elements and best practices, network designers can develop a robust network architecture that not only meets the current needs but is also adaptable to future challenges. Designing for security in computer networks. Designing for security in computer networks is an essential practice that involves designing for and implementing various measures to protect the network's integrity, availability, and confidentiality. In today's interconnected world, networks are constantly exposed to a variety of threats ranging from data breaches to unauthorized access and cyber attacks. Therefore, security must be an integral part of the network design process rather than an afterthought. By establishing stringent security standards from the beginning, organizations create a robust defense mechanism that safeguards not only the network itself but also the data and applications that reside on it. Building a comprehensive security posture involves a multi-layered approach that encompasses hardware, software, policies, and even human factors. An illustration of a shield with a locked padlock surrounded by computing devices. The devices are connected by lines, which represent logical network connections. Hardware security, keeping routers, modems, and network adapters safe. From identity theft to lost revenue, the consequences of data breaches and cyber attacks are severe. Because data flows over networks, keeping data safe starts with keeping network hardware devices secure and preventing threats to network traffic. The global average cost of a data breach in 2023 was $4.45 million. Source: Cost of a Data Breach Report 2023, opens in a new tab, by IBM. When you hear the term cybersecurity, you might immediately think of creating stronger passwords and blocking phishing attacks. These measures are very important. However, for an IT support technician, cybersecurity encompasses much more, from securing network hardware to protecting the software individuals use to access networks. A person entering a number code on a lock keypad. Image source: photo by Emma Wegman, opens in a new tab, on Unsplash, opens in a new tab. Let's explore common threats to networks and some design principles to secure networks. Threats to hardware. Networking hardware, like other systems, face a range of security threats that could compromise their integrity, availability, and confidentiality. When IT support technicians understand these threats, they take precautionary measures, identify security issues, and secure hardware. Physical attacks. Unauthorized individuals can physically access networking hardware like routers, switches, or servers to steal data or disrupt services. When unauthorized individuals gain physical access to these devices, they can alter the hardware configurations, install malicious software, or even implant hardware-based keyloggers and other spying devices. A keylogger is software that records every character that someone types on a device so the attacker can extract sensitive information, such as passwords, from it. Such attacks can compromise the entire network's integrity, as these devices are crucial points for data routing and management. Organizations use the following design principles to secure network hardware against physical attacks. Keep servers and other network devices in a room with a lock, passcode, or ID swipe system. Install security cameras near network hardware. Secure other network devices, such as modems, routers, and bridges, in cages with locks, cabinets, and hard-to-reach locations. Firmware attacks. Hardware, like routers and modems, has special programmed code embedded into their memory called firmware. The firmware runs when the device powers up and controls how the hardware operates. When attackers successfully compromise a device's firmware, they gain deep access to the device's functionalities and, by extension, the broader network. This level of control allows them to reroute network traffic, capture sensitive data, or even disable the device entirely, disrupting network services. In some cases, attackers also use compromised firmware as a launching pad for attacks on other devices within the network, thereby escalating the level of threat. Organizations use the following design principles to secure network hardware against firmware attacks. Keep firmware up to date and download updates or patches directly from the manufacturer's website. Divide the network into smaller, isolated segments to contain the impact of a compromised device, limiting the spread of an attack within the network. Implement intrusion detection systems and intrusion prevention systems to monitor for unusual network activities. Device spoofing. Device spoofing is a security threat in which an attacker replaces a genuine network device, such as a router or a switch, with a malicious counterpart. The attacker configures the rogue device to mimic the behavior of the legitimate device it replaces, making it difficult to detect the change immediately. Organizations use the following design principles to secure network hardware against device spoofing attacks. Limit physical access to network devices to authorized personnel only, using locked rooms, cabinets, or cages. Implement strong authentication protocols for devices connecting to the network, such as MAC address filtering or digital certificates. Regularly audit network devices and configurations to ensure they match expected settings and inventory. Now that you've explored ways to protect the physical devices that make up a network, let's explore another important aspect to network security: keeping data safe as it moves across the network. The data that travels across the network, be it confidential business information, personal data, or financial transactions, also faces a range of threats. Threats to network traffic. As data moves from one device to another on a network, it becomes vulnerable to unauthorized access, interception, and even alteration. A robust network must protect both its physical devices and the data that flows through them. Let's examine the vulnerabilities that affect network traffic and strategies to keep data secure as it travels through the network. Denial of service, DoS, attacks. A denial of service, DoS, attack floods a network with excessive requests, making it unavailable to users. If you've ever experienced a traffic jam on a highway, you have a sense of what a DoS attack aims to do to computer networks. These attacks often target well-known entities like government websites, banks, or social media platforms. Sometimes, they even serve as a smokescreen for other types of attacks that happen simultaneously. Some common types of DoS attacks include buffer overflow. A buffer overflow attack on a network aims to exploit vulnerabilities in network services or protocols by sending excessive data to a buffer, a temporary storage area in a network device like a router, switch, or server. The goal is to fill the buffer with more data than it can hold, causing an overflow into adjacent memory spaces. Internet Control Message Protocol, IMCP, flood. An ICMP flood targets a network by overwhelming it with ping requests. The objective is to consume the target network's bandwidth and resources, making it difficult or impossible for legitimate users to access or use the network services. Synchronize, SYN, flood. An SYN flood aims to make a server, network, or service unavailable by overwhelming it with incoming connections. Think of this as someone constantly ringing your doorbell but running away. When a threat actor attacks a network with a SYN flood, the servers that are connected to the network get flooded with incomplete connection requests, leading to a crash. Organizations use the following design principles to keep data secure against DoS attacks. Implement controls to limit the number of requests a user can make within a given time frame, making it more difficult for an attacker to flood the network or server. Configure firewalls to filter out malicious or unnecessary traffic, including known attack patterns or IP addresses. Use monitoring tools to analyze network traffic patterns and detect unusual spikes or anomalies that might indicate a DOS attack. Distributed denial of service, DOS, attacks. A distributed denial of service, DOS, attack is a coordinated DOS attack that uses a large group of compromised computers known as a botnet instead of one computer. The botnet makes it harder to trace the origin of the attack and more devastating in impact. Organizations use the following design principles to keep data secure against DOS attacks. Design the network and servers for easy scaling to handle surges in traffic and distribute the load. Utilize specialized services that can absorb and mitigate the impact of large-scale DOS attacks, acting as a buffer between the attacker and the target network. Employ machine learning or statistical models to detect anomalous behavior in network traffic, which can indicate a DOS attack in progress. Eavesdropping attacks. An eavesdropping attack, also known as a man-in-the-middle attack, is when a threat actor secretly intercepts and possibly alters data transmission between two parties. These types of attacks are like eavesdroppers listening in on your network conversations. Imagine you're talking to a friend, but someone is secretly listening in without either of you knowing. In this digital scenario, there are three parties: the sender, the user, the receiver, and the eavesdropper, the attacker. Some common types of eavesdropping attacks include physical attacks. In this type, the attacker is physically near the sender or receiver. For example, the sender and attacker are both connected to the same public Wi-Fi at a coffee shop, or the attacker set up a fake Wi-Fi network as a trap. The attacker then listens to the network traffic to find out what the sender is doing online. This attack could include stealing passwords or other personal information. Logical attacks. With a logical attack, the attacker doesn't have to be near the sender. They might send the sender an email or text message with misleading links. Clicking on one of these links takes the sender to a fake website designed to steal their information. Replay attacks. A replay attack occurs when an attacker intercepts the transmission of data, for example, login details, and then retransmits it, for example, to log into the network on their own device. Think of a replay attack like someone recording a conversation between you and a friend and then playing it back later to trick someone else. Organizations use the following design principles to keep data secure against eavesdropping attacks. Use secure communication protocols like HTTPS and secure VPNs to protect data as it traverses the network. Use strong encryption protocols for data at rest and in transit to make it difficult for eavesdroppers to decipher intercepted information. Ensure that only authorized users can access sensitive data by implementing multi-factor authentication and strict access controls. Hijacking attacks. In a hijacking attack, the intruder takes over an already established connection between a user and a trusted entity. In the online world, trusted entities, like verified users or secure websites, use access tokens as digital ID cards to prove their legitimacy. However, attackers can steal these tokens by secretly observing data exchanges between these trusted parties. Once they have a token, they can impersonate the trusted entity, altering information, or even accessing private accounts as if they were the legitimate user. Imagine you are logged into your email account, and suddenly, someone else takes control of it. Now, they can send emails as you, read your messages, and even change your account settings. Organizations use the following design principles to keep data secure against hijacking. Implement secure session handling to ensure that once a user logs in, attackers cannot easily hijack the session. Create isolated network segments to contain critical data and services, making it harder for attackers to move laterally after gaining initial access. Employ multi-factor authentication methods to confirm the identity of users, reducing the likelihood of account hijacking. Building a network that is secure against external attacks by threat actors is one way to ensure a robust networking environment. Next, you'll explore how network engineers make networks resilient by enabling them to recover from failures and provide enough bandwidth for all users when they need it. While IT support technicians might not be involved in building resilience into networks, they are responsible for making sure the network stays resilient and for continually monitoring the network and addressing problems. Designing for resilience in computer networks. A dashboard needle pointing over the word efficient and a network of lines and dots. A resilient network can adapt, recover, and often heal itself to ensure continuous and reliable communication. Network resilience refers to the ability of a network to continue functioning efficiently even when it faces disruptions, challenges, or attacks. Think of network resilience as similar to a robust immune system that helps fight off illnesses. Hardening networks against attacks. To improve resilience, network architects use a process called hardening to protect networks against various types of attacks. Hardening is the process of securing a system by minimizing vulnerabilities and potential points of failure. Network administrators apply some hardening procedures directly to network hardware. Other hardening procedures apply to the devices the network connects to. By hardening devices, networks can securely deliver data to them. This process makes the network more resilient. Review the following to learn about technologies and methods organizations can use to harden a network. Firewall. Firewalls are security devices that act as barriers between a network and potential threats from the outside world. A firewall uses predefined rules to decide which data packets are allowed to pass through and which are to be blocked. By doing so, it helps protect the network from unauthorized access and potential cyber threats. Think of the firewall as a filter that separates your network from the wider internet, only letting in what's deemed safe. Intrusion Detection System, IDS. An intrusion detection system, IDS, monitors traffic for suspicious activity and flags it for review. An IDS is like a surveillance camera for your network. It constantly monitors the traffic flowing through the network for any unusual or suspicious activity. If it detects something that matches known patterns of cyber threats, it sends out an alert for further investigation. Multi-factor authentication, MFA. Multi-factor authentication, MFA, is a security method that requires users to provide two or more forms of identification before granting user access to an account or system. Instead of just asking for a password, MFA can also require something like a user's fingerprint scan, a temporary code that's sent to a user's phone, or a security question. By requiring two or more forms of verification, unauthorized access becomes much more difficult. Data backup. Regularly backing up data ensures that organizations can restore their important information in case of data loss due to an attack. How often they should back up data depends on many factors, including the types of data being stored, organizational policies, and regulatory laws and requirements. Training. Educating those who use the network about the importance of cybersecurity can go a long way in preventing attacks. Many organizations provide organization-wide training to their employees on how to identify threats and what to do in the case of an attack. Networks that recover from failures and heal themselves. Hardening is one way to create a resilient network. But resilience means more than just being resistant to attacks. A network is also resilient when it can recover from failures. Balance data transmission loads so data transfers are distributed more evenly across the network. Use built-in redundancy in case a part of the network fails. Let's learn about how networks recover from failure and heal themselves. Failover systems. In case of a hardware or software failure, networks switch operations to a backup system automatically, ensuring minimal disruption. Load balancing. When there is too much traffic, the network can distribute the load among multiple servers to prevent overload and maintain optimal performance. Self-healing architecture. Some advanced networks have self-healing capabilities that can automatically reroute data through alternative paths if the primary route fails. Automatic monitoring. Networks have automated monitoring tools integrated within the network to identify issues and initiate corrective actions without human intervention. Employing redundancy. Duplicated critical components allow networks to continue to function even if one part fails. This redundancy is similar to having multiple engines on an airplane that allow it to keep flying even if one engine fails. Scenario: network resilience in the real world. Building resilience into a network involves all the techniques you learned about working together. A resilient network prevents or recovers from attacks, recovers from failures, and heals itself when part of the network has a problem. These techniques apply to both LANs and WANs, although how they're applied can differ. While a network architect is responsible for designing a resilient network, it's up to the IT support technician to ensure the resiliency measures are working and to maintain the network as it's running. Let's follow the ways MET, an IT support technician, ensures a network remains resilient. Introduction. A woman standing by multiple monitors displaying data in different visualizations and charts is working on a tablet. As the senior IT support technician at Multinet Corp., MET is responsible for ensuring that the extensive network is robust and resilient. She knows that in the fast-paced world of a large, global corporation, even a momentary glitch can translate into significant losses. Step 1. Implements regular updates and audits. One of MET's first tasks each morning is to ensure all software and hardware are up to date. A blinking notification on her device indicates that a security patch is available for one of the servers. MET promptly installs the update, aware that even a small vulnerability could open doors for attackers. Every month, she also conducts security audits, meticulously scanning the network to identify any weak points. Step 2. Checks the firewall and intrusion detection system, IDS. MET reviews the logs from the company's firewall. This digital barrier acts as the first line of defense against potential cyber threats by filtering incoming and outgoing traffic based on predefined rules. Along with firewall metrics, she keeps an eye on the intrusion detection system. The IDS constantly watches for signs of abnormal activity. Today, it flags a suspicious login attempt from an overseas IP address. MET investigates and finds it to be a false alarm, a remote employee who forgot to use the company VPN. She makes a note to add this incident to the training materials for staff. Step 3. Helps users set up multi-factor authentication, MFA. Multi-factor authentication is another crucial layer in her defense strategy for the company. MET receives a message from an executive who is having trouble with setting up MFA. A quick, remote troubleshooting session resolves the issue. She knows that MFA significantly reduces the likelihood of unauthorized access to her company's sensitive information. Step 4. Takes LAN-specific measures. Within the corporate office's LAN, MET focuses on physical security measures. She regularly checks the biometric access system to the server room to ensure it is functioning correctly. She also closely monitors the health and performance of each network segment that the architect initially set up. This measure includes updating firewalls specific to each segment, running vulnerability scans, and checking for unusual traffic patterns that could signify a problem. By doing so, MET ensures that if a security issue arises in one part of the network, it can be contained and not spread to other areas, thereby maintaining the LAN's resilience. Step 5. Takes WAN-specific measures. For the WAN, which connects Multinet Corp's global offices, MET has a different set of tasks. While the network architect initially configured the encryption protocols, it is up to MET to regularly review them to ensure they are still up to date with the latest security standards. She also manages VPN access for remote employees, frequently checking logs to spot any signs of unauthorized or suspicious activity. This active monitoring helps ensure that data transmitted across large distances remains secure and that remote employees can safely access the network. Step 6. Monitors redundancy and failover systems. Lastly, MET verifies that the failover systems are operational. These backup systems automatically kick in if there is a hardware or software failure, keeping the network running smoothly. As she wraps up her day, MET knows she has fortified the network against potential disruptions and threats. Now that you've learned about network resilience, let's explore the ways that designing for scalability improves networks. Designing for scalability in computer networks. Scalability is a crucial aspect of network design and maintenance that allows a network to grow and adapt to changing needs. The network architect usually focuses on scalability during the initial design while taking into account many factors that impact scalability. Factors external to the network. Imagine a national gardening chain whose network was initially designed to handle the data and user load of its 50 physical stores. However, when the company launched a highly successful online marketplace and gardening app, they experienced an unexpected surge in data volume and user traffic. The network was suddenly tasked with managing real-time inventory updates from both in-store and online sales, as well as user data from the app. Despite several attempts to upgrade the system, the network could not efficiently adapt to the rapidly changing external factors, such as the increased number of users and the vast amount of data being transferred. The company found itself falling short in meeting regulatory requirements for online data security and started experiencing latency issues, impacting customer satisfaction and, ultimately, sales. A garden shop showing a service counter and shelving at the back, hanging baskets from the ceiling, and greenery around the edges in the foreground. So, what happened? This gardening chain experienced external impacts to its network. Let's explore some of the external factors that can impact a network's ability to scale. User growth. An increase in the number of users and devices connecting to the network can significantly impact its performance. As more people join the network, they consume more resources, which can lead to slowdowns and congestion. Data volume. Beyond the number of users, the actual amount of data being transmitted also affects scalability. Networks need to be designed to handle increasing volumes of data efficiently. Regulatory requirements. Legal and industry standards dictate the need for specific types of data handling or security measures. Compliance with these regulations might require network adjustments that impact scalability. Technology trends. Emerging technologies, such as Internet of Things, IoT, devices or new data transmission protocols, necessitate changes in the design of a network to ensure it remains scalable. Understanding external factors that influence network scalability enables IT support technicians to pinpoint potential network issues for the architects to address. Along with external factors, there are also internal factors. Let's explore those next. Factors internal to the network. To ensure that a network is scalable, a network architect identifies internal factors. These factors are inherent to the design or hardware of the network that impact the ability for a network to scale. Internal factors that can impact a network's ability to scale include hardware capabilities, software configurations, and design topology. Hardware. Networking hardware has limits on processor speed, storage, and memory, which can restrict how much the network can grow. Software. The software that manages the network and the protocols that govern data transmission impact scalability. Using software that is compatible with a range of hardware or that allows for centralized configuration management makes it easier to scale the network, as changes can be rolled out quickly and uniformly. Network topology. The structure of the network, how different nodes are interconnected, plays a critical role in scalability. Some topologies are easier to expand than others. Redundancy and failover. The presence or absence of redundant systems and failover capabilities can either bolster or hamper scalability. Networks designed with these features quickly adapt to increased load or system failure. Virtualization. The ability to create virtual versions of hardware, platforms, and storage can greatly impact scalability. Virtualization allows for more efficient resource utilization and easier management as the network scales. Quality of service, QoS, settings. These settings prioritize certain types of traffic over others. Incorrectly configured QoS can lead to performance issues as more devices and types of data join the network. Security features. While necessary for protecting the network, overly complex or outdated security measures can impede scalability by adding latency or compatibility issues. Internal and external factors influence scalability. from hardware limitations to evolving technology trends. By understanding these factors, the individuals responsible for either designing or maintaining a network ensure that it remains robust and adaptable to changing needs. Design principles for a scalable network. Designing a scalable network means ensuring that the network can handle growth in users, devices, and applications without a decline in performance. Whether an organization is expecting a gradual increase in demand or preparing for sudden spikes, adhering to robust design principles leads to a more resilient network in the future. Let's explore the primary design principles for a scalable network. Modularity means dividing a network system into separate, independent components or modules, each responsible for a specific functionality. These modules can function on their own but can also interact with other modules when necessary. Modularity allows organizations to upgrade, scale, or modify parts of the network without impacting the entire network. For instance, if the network needs more storage space, they can add a server without impacting other parts of the network. Scalable addressing and routing means setting up IP addressing and router configurations to handle growth. For IP addresses, it means there are sufficient unused addresses for new devices. And consistent addressing patterns to make it easier to identify devices, determine their roles and troubleshoot issues. For routers, it means using protocols to limit unnecessary traffic and quickly determine the most optimal path for network traffic. Quality of service, QoS, involves establishing the policies and mechanisms that work together to ensure specific data traffic gets the appropriate level of priority. In an environment where multiple applications and devices compete for network resources, not all data are created equal. For instance, a video conference call might be deemed more critical than a file download and, thus, would be allocated more immediate resources to maintain smooth video quality. QoS ensures that such critical applications receive the bandwidth and response times they need, guaranteeing their optimal operation. This becomes increasingly important as the volume of network traffic surges, with the potential for congestion and slowdowns. Configuring QoS policies appropriately helps organizations maintain high standards of network performance, even as network traffic grows. Cloud computing and virtualization empower organizations to scale swiftly based on changing demands. Cloud computing offers a platform where resources, like storage, are delivered over the internet rather than requiring local hardware. This on-demand availability ensures that networks can scale up or down based on immediate requirements without the capital-intensive process of procuring and setting up physical network hardware. Virtualization separates software from hardware, enabling multiple virtual systems to run on a single physical machine. This optimizes resource utilization, as one server can now host multiple virtual environments, each tailored to specific needs. When networks are designed for scalability, IT support technicians spend less time troubleshooting network issues. Designing scalable systems involves implementing effective principles such as modularity, scalable addressing and routing, quality of service, QoS, and the integration of cloud computing and virtualization to adapt to growth and changing demands. Case study, ABC Company. Employability skills. Analytical thinking. Read the following case study for ABC Company. Then, you'll complete an activity. Background information. ABC Company is opening a new corporate headquarters and is designing the network for their new offices. Recognizing the importance of a robust network, the company decides to design a network that not only meets its current needs but also anticipates future expansion and challenges. The company is considering three primary elements as part of the network design: security, resilience, scalability. For ABC Company, having a robust and efficient network means they can reliably serve their customers, protect sensitive data, and adapt to changing market conditions. They don't want a poorly designed network because it can lead to vulnerabilities, costly downtime, and limit the company's growth. Designing a secure network. IT management and network architects at ABC Company begin by considering the security threats that the company faces. They know that their network hardware must be secured, so they plan to install their servers and network devices in a locked room with a keypad on the door with surveillance cameras monitoring the door and the room. For network devices that are not in the locked room, the team is concerned with device spoofing. To counteract device spoofing, ABC company plans to implement MAC address filtering. They also understand that as data travels between devices, it's exposed to a range of threats, such as DDoS attacks and eavesdropping. For threats to network traffic, ABC company plans to use firewalls and monitoring tools to detect and filter malicious traffic. They also plan to use a statistical model to detect irregular behavior in network traffic. Finally, they will use secure communication protocols and encryption, with multi-factor authentication, to ensure only authorized access to data, making sure the network is resilient. In the event of an attack, the team knows that the company's network needs to be resilient. They are planning on hardening techniques, such as installing intrusion detection systems, regularly backing up data, using a failover system so that the network can automatically switch to a backup in the event of failure, keeping the network scalable for growth. Finally, ABC company plans for a large amount of growth over the coming years, so scalability is a key factor in their network design. They are launching a new application that uses augmented reality and expect both a large increase in users and a large increase in the amount of data they are processing. They are planning on choosing modular network designs to allow for easy expansion without overhauling the entire system. Investing in cloud solutions, which provides flexibility in terms of storage and computing power. Evaluate your thinking. Does your answer account for the following? Security. ABC company plans to install their servers and network devices in a locked room with a keypad on the door with surveillance cameras monitoring the door and the room. They are also implementing MAC address filtering to prevent device spoofing. In addition, they plan on using firewalls, monitoring tools, and a statistical model to detect irregular network behavior, along with secure communication protocols, encryption, and multi-factor authentication. ABC company should also keep firmware up to date and divide the network into smaller, isolated segments. Resilience. ABC company is planning to install intrusion detection systems and regularly back up data. They are also planning to use a failover system so that the network can automatically switch to a backup in the event of failure. They should also add duplicate critical network hardware components. And they should also train their employees on cybersecurity threats. Scalability. To ensure scalability, ABC company is implementing modular network designs and investing in cloud solutions, which provide flexibility in terms of storage and computing power. ABC can also configure its quality of service, QoS, settings to ensure the correct data receives priority and design a scalable IP addressing and routing structure. Summary and looking ahead. You learned a great deal about network design principles in this lesson to keep networks robust in the face of various security threats to network hardware and traffic. You learned about network resilience, hardening, and factors that can impact the resilience of networks. You can identify design principles to ensure a computer network's security, resiliency, and scalability. Get ready to dive deeper into network design. In the next lesson, you will explore the significance of recording and documenting a network design. You will discover the types of network designs and the steps to create one. You will also learn about the essential components of a configuration file. About this lesson, network documentation. In this lesson, you'll learn why comprehensive documentation is vital for network design and management. You'll explore the types of network design documentation and the steps to create a diagram. You'll also learn about the configuration files that control networking hardware and policy documents that establish guidelines for building out networks. Network design documentation. It's a best practice is to document network design during the network design process. Then, the documentation acts as the cornerstone for efficient network management. Documenting a network's design includes details such as the location of devices, the types of cables that the network uses, and wireless settings that can get lost if they're not captured during the process of designing and implementing the network. A woman sitting at a table working on documents with a laptop and a monitor. Let's explore some of the ways that network design documentation helps individuals who implement the network and individuals who maintain it. Select each section to learn more about the benefits of documenting network designs. Aids in troubleshooting. When issues arise, having a well-documented network speeds up the process of identifying problems and implementing solutions. The documentation serves as a reference point for what the network should look like, enabling quick resolution of issues. Facilitates communication. Documentation serves as a universal language that bridges the gap between technical and non-technical stakeholders. It helps everyone understand the network's structure and functionality, fostering informed decisions. Streamlines maintenance and upgrades. A documented design simplifies regular maintenance tasks. Knowing where each component fits and how it functions makes it easier to upgrade systems and incorporate new technologies. Ensures business continuity. In the event of system failures or personnel changes, documentation serves as an invaluable guide for restoring services and bringing new team members up to speed. Assists in compliance and auditing. Many industries require adherence to certain standards and regulations. Documentation provides the necessary evidence to demonstrate compliance during audits. Future-proofs the network. As businesses evolve, so do their networking needs. Detailed documentation provides a foundation upon which to plan and implement scalable solutions for the future. Enhances security. Documentation helps in creating a secure environment by clearly outlining the network's layout and protocols, making it easier to spot vulnerabilities and unauthorized changes. Improves cost efficiency. Through accurate and detailed documentation, businesses avoid redundant investments in hardware and software, as well as minimize downtime by streamlining troubleshooting and maintenance. Preserves knowledge. Documenting the network design ensures that institutional knowledge is not lost when key personnel leave or new team members join. Documenting a network design equips a business with the tools needed to operate, manage, and grow in a methodical and efficient manner. It lays the groundwork for smooth communication, effective problem solving, and long-term strategic planning. Types of network design documentation. Because networks are so complex, network architects use various tools and document formats to capture key aspects of the network. The type of document tool and method an architect uses depends on what part of the network they're documenting. Select each tab to learn more about types of network design documentation. Network diagrams. Network diagrams provide a visual representation of the network's architecture, showing how different devices and cables are connected. Diagrams make it easier for network architects, network administrators, and IT support technicians to understand how each component fits together. They visualize the network's complexities to support network design, network installation, and network troubleshooting. Network diagrams are typically produced using diagramming tools such as Microsoft Visio or Lucidchart. But, they can also be produced using network simulator tools such as Cisco Packet Tracer. Configuration files. Network architects and administrators use these text-based records to configure, deploy new devices, and keep a record of settings for each network device. They also serve to help IT support technicians in troubleshooting, as examining the configuration files can provide clues to the root cause of an issue. Also, they ensure that network administrators can easily reset or replace devices in the event of a failure. Configuration files are typically produced in the command line interface, CLI, or system settings of a particular device. They can also be managed and deployed in network management systems. User stories and use cases. These documents describe how the network will be used, outlining requirements and expected outcomes. They help in understanding the network's purpose and can guide future decisions. User stories act as a narrative that guides the network's functionality. They articulate the needs of end users and serve as a benchmark for success. Use cases and user stories can be created in any text-based tool, such as a word processing software or spreadsheet software. There are also agile project management tools where user stories and use cases can be created and managed. Asset list and inventories. Knowing what hardware and software are part of the network simplifies management tasks and helps ensure all components remain up to date. These lists and inventories serve as a comprehensive catalog. They streamline maintenance and assist in budget planning for upgrades or replacements. Policy documents. These documents outline rules for network usage, specifying what is allowed and what is not. This documentation ensures consistent practices, facilitates security, and aids in maintaining optimal network performance. IT support technicians might often need to reference network policy documents when setting up or decommissioning devices or in the event of a security incident. Common policy document types include acceptable use policy, security protocols, access control policy, and disaster recovery procedures. Documentation of a network design isn't merely a management necessity. It's a vital part of ensuring that the network serves its intended purpose efficiently and securely. Different types of documents contribute to this goal, from providing a visual overview to setting usage policies. Next, let's explore network diagrams in more detail. Network diagrams. A network diagram is a visual representation that outlines how different devices and cables are connected to form a network and how data flows between these devices. Professionals use these diagrams to plan, implement, and troubleshoot networks, much like an architect uses a blueprint to construct a building. A network diagram helps IT support technicians by enabling quicker problem resolution and helping in making informed decisions about upgrades or modifications. A network diagram is a visual representation of the network topology. Recall that a topology is the physical or logical layout of the network. Key components in a network diagram. In a typical diagram, several typical components are included. Some of the components include the following. Nodes. Nodes are the devices that are in the network, such as computers, servers, and switches. Links. Represented often as solid lines or dotted lines in a diagram, links indicate the connections between nodes. Type of network. The diagram will specify whether it's a local area network, LAN, a wide area network, WAN, or another variant. Subnets. If the network is segmented into subnets, each of the subnets will also be indicated. Firewalls and security devices. These components show how the network is safeguarded. External connections. These connections are displayed where the network connects to external systems or the Internet. Notice the example network diagram below. In this simplified network diagram, each of the nodes are connected to other parts of the network by a logical network connection. All data flows to and from servers and the Internet through routers and switches. A network topology diagram showing nodes as computer monitors, a subnet with two nodes, a router, a server, a firewall, and the Internet. All items in the diagram are connected with lines representing network connections. Now that you've explored the typical components of a network diagram, review the steps to create a network diagram. Creating a network diagram. Typically, the responsibility of creating a network diagram falls on network engineers, architects, or IT managers who have an intricate understanding of the network's architecture and operations. But, in smaller organizations, specialized roles like network engineers or architects might not exist. In such scenarios, IT support technicians often have multiple roles and could be responsible for designing and documenting the network. And in organizations where IT support technicians are not involved in creating network diagrams, having the skills to be able to read them will help them to address some of the network issues they encounter. Creating a network diagram involves 4 steps. 1. Take an inventory. 2. Add devices and cables. 3. Add labels and annotations. 4. Review and update. Introduction. Let's explore the 4 steps of creating a network diagram. Step 1. Take an inventory. A document with a list and check marks on a laptop computer. Begin by listing all the network devices, connections, and configurations. Ensure the list includes all devices like routers, switches, servers, printers, desktops, and laptops. Make note of their make and model, IP addresses, and how they're connected. Step 2. Add devices and cables. A network diagram with no labels, showing network diagram symbols such as a cloud for the Internet, a brick wall for firewall, and an icon that represents a desktop. Add devices to the diagram and connect them using lines to depict cables. Use standardized symbols for different types of devices for easy understanding. Common standard symbols include: a cylinder shape represents a database. A cloud shape represents the Internet. A brick wall represents a firewall. A rectangle shape represents general-purpose computers. A circle with 4 arrows represents a router. A box with 2 double-sided arrows intersecting represents a switch. Take a moment to zoom in on the example network diagram above to review the devices and cables. Step 3. Add labels and annotations. A network diagram with labels showing network diagram symbols such as a cloud for the Internet, a brick wall for firewall, and an icon that represents a desktop. The connection between the router and 2 switches is labeled as Ethernet. Label all nodes and links and add any relevant notes. One example is to label a link between a computer and a switch as Ethernet connection and annotate it with details like 100 Mbps. Label nodes with names or IP addresses for easy identification. Take a moment to zoom in on the example network diagram above to review the labels. Step 4. Review and update. An illustration of a man holding a magnifying glass up to a laptop to review a network diagram on the screen. Network requirements can change, so regularly review and update the diagram to reflect the current state of the network. Now that you've learned the 4 steps of creating a network diagram, let's explore the components of configuration files and how to read them. Configuration files. At the heart of many networking hardware devices is the configuration file, or config file. These files contain the instructions and settings that determine how a piece of networking equipment interacts with other devices, routes data, and enforces security protocols. They are like the DNA of the device, influencing its behavior and role within the broader network infrastructure. Instead of diving deep into the hardware every time a modification is needed, network administrators and IT support technicians can simply refer to these configuration files to tailor functionality to their needs. Components of a networking hardware config file. Let's explore the basic components of a networking hardware configuration file. Device identification. The file includes details like device name, location, and description to help in identifying the device within a network. Interface settings. A configuration file explains how each interface, like an Ethernet port, on the device is configured. This can include IP addresses, subnet masks, and operational statuses. Routing protocols. These are the settings related to how the device routes data, including protocols and their respective configurations. Security settings. The file includes information about configurations like access control lists, firewall settings, VPN configurations, and other security-related parameters. VLAN configurations. A configuration file includes details on how virtual local area networks are set up and managed. Redundancy and failover. Configurations related to ensuring high availability, such as Virtual Router Redundancy Protocol, VRRP, settings, are documented. VRRP is a protocol designed to allow 2 or more routers to work together in such a way that if one router fails, the other can seamlessly take over, ensuring uninterrupted network access. Management settings. A configuration file includes information on how the device can be accessed and managed, including monitoring configurations and logging settings. Comments. Embedded notes and comments within the configuration explain and provide context about specific settings, often starting with symbols such as or number. The following is an example of a configuration file for a modem. This example includes information about each of the components that you just learned about, in sequential order, such as number device identification. Take a moment to review it in detail. Some configuration files, but not all, might look exactly like this. Some config files will not include some of these components, and others will include multiple sections of the same component. And config files might not include these components in this order. Number device identification. Device _name, Office Modem 001. Location, 3rd floor, room 312. Description, main modem for 3rd floor office area. Number interface settings. Interface Ethernet 0/0. IP_address, 192.168.1.1. Subnet_mask, 255.255.255.0. Status, up. Number routing protocols. Routing_protocol, OSPF. Router_ID, 1.1.1.1. Network, 192.168.1.00.0.0.255 Area 0. Number security settings. Access_list 101. Permit IP 192.168.1.00.0.0.255 any. Firewall. Enable, true. Inbound_rule, block all. Inbound_rule, allow from 192.168.1.0/24. VPN. Type, IPsec. Pre_shared_key, S3CR3TK3Y. Number VLAN configurations. VLAN 10. Name, HR department. Ports, Ethernet 0/1 to Ethernet 0/5. Number redundancy and failover. VRRP1. IP_address, 192.168.1.254. Priority, 100. Master, true. Track_interface, Ethernet 0/0. Number management settings. Management_access, SSH, HTTPS. Monitoring. SNMP_enable, true. SNMP_community, public read. Logging. Server, 192.168.1.10. Level, warnings. Number comments. Number This configuration was last update on February 2, 2024 by Network Admin. Number Remember to back up the configuration after making changes. Now that you are familiar with the components of a networking hardware configuration file, you're ready to try out an activity. Policy documents. Policy documents are a critical component of network design and management. They provide structured guidelines, ensuring the consistent operation, security, and maintenance of network resources. By setting clear expectations and procedures, these documents aid in risk management, regulatory compliance, and ensure a harmonious relationship between users, network administrators, and IT support technicians. A person points at one binder on a shelf with several binders. The following are some of the most common types of network policy documents. An acceptable use policy, AUP, specifies what users are and aren't allowed to do with the organization's IT resources, including networks, devices, and data. AUPs include information about who the policy applies to, such as employees, contractors, and visitors. They also specify prohibited activities, such as illegal downloads, visiting malicious websites, or using resources for personal gain. Finally, they outline the consequences or actions taken if the policy is violated. Security protocols outline the measures and practices implemented to safeguard the network's integrity, confidentiality, and availability. This includes policies on inbound and outbound network traffic, firewall rules, guidelines for encrypting data, and authentication methods. These documents also contain a schedule and instructions for security audits to identify potential vulnerabilities. Access control policies govern who can access which parts of the network, ensuring that users only access what they need to fulfill their roles. This policy defines different user categories, such as administrator, user, or guest, and what data each category can access. They also describe how users prove their identity, such as passwords, biometrics, or multi-factor authentication. Access control policies might also contain access review schedules and logging and monitoring information. Disaster recovery procedures outline the steps to recover and restore network operations after a significant adverse event, whether it is a cyber attack, natural disaster, or human error. They include the identification of potential threats and their impact on the network and guidelines on how and where data is backed up, including frequency and retention policies. They also outline recovery plans, which include details about communication to stakeholders. Summary and looking ahead. In this lesson, you learned about the best practice of documenting network design during the network design process and using it for efficient network management. You learned about different types of documentation and then focused on the components and steps to create network design diagrams. You also learned about networking hardware configuration files and had the opportunity to observe their components in a realistic example. You've completed the final lesson of this module. Next, you'll review the module's key points and explore additional resources related to network design. Points to remember. Key concepts. 1. Network topology provides a structured layout showing how network components connect and how data flows between them. It helps IT support technicians efficiently resolve network issues. 2. Physical topologies like bus, star, ring, mesh, and hybrid have distinct advantages and disadvantages for network design. 3. Logical topologies like point-to-point, client-server, and VLAN determine how data flows between connected devices on a network. 4. Understanding network design and topology helps IT support technicians optimize and suggest improvements to network performance. 5. When designing a network, businesses determine the type of topology to meet their requirements for security, resilience, and scalability. 6. Potential security threats include physical attacks, firmware attacks, eavesdropping, and hijacking. Network design principles help mitigate security risks. 7. Hardening techniques like multi-factor authentication and data backups enhance resilience against attacks. 8. Network resilience refers to adapting and recovering from disruptions. Resilience strategies include load balancing, failover systems, and redundancy. 9. Internal and external factors impact network scalability. A scalable network handles growth without performance decline. 10. Modularity, quality of service, and virtualization facilitate network scalability. 11. Network diagrams visualize network architecture to aid planning, implementation, and troubleshooting. They include elements like nodes, links, subnets, and firewalls. 12. Creating a diagram involves 4 steps. Take an inventory. Add devices and cables. Add labels and annotations. Review and update. 13. Configuration files contain settings and instructions that determine how networking hardware operates. 14. Policy documents, like acceptable use policies, AUPs, and disaster recovery plans, provide network usage and maintenance guidelines. Big ideas. In addition, you explored or practiced these skills. Employability skills. Growth mindset. Reflect on interests and skills to identify areas of the network design process to learn more about. Critical thinking. Identify the appropriate physical and logical network topology to use in a scenario. Identify the type of attack occurring in a scenario. Identify design principles organizations use to protect network hardware against physical attacks. Analytical thinking. Analyze a case study and identify the design principles used for security, resiliency, and scalability. Select design principles to ensure a computer network is secure, resilient, and scalable. Review a configuration file to determine what components are represented. Attention to detail. Examine the design, devices, and connections in a network diagram. Review configuration files and determining the components that part of the file represents. Learning objectives. Now that you've completed this module, you should be able to explain the characteristics and configurations of common physical and logical network topologies. Choose a network topology given a scenario. Select design principles to ensure a computer network is secure, resilient, and scalable given a case study. Describe the benefits and components of network design documentation, including network diagrams, networking hardware configuration files, and policies. Explore more resources. To explore concepts covered in this module in more depth, check out these resources. What is networking? Opens in a new tab. This resource by IBM is an introduction to computer networking, covering the basic concepts, types, components, architectures, topologies, protocols, security, and applications of networks. Achieving Network Resilience by Design, opens in a new tab. This blog by Scott Lienebarger for AT&T Business explores what network resilience is, what makes a network resilient, and steps to ensuring a resilient network. One-stop guide to understanding what network topology is, opens in a new tab. A video lesson by Anmol Kapoor for Simplilearn is about network topologies and factors that affect the choice of which to use. Types of network topology: bus, ring, star, mesh, tree diagram, opens in a new tab. This GURU99 resource by Lawrence Williams covers the different types of network topologies, their advantages and disadvantages, and how to choose the best one for a given network.